let's say the distance here is 1 millimeter. Let's call it R. And between here, R is also 1 millimeter. Technically, this is R13, and this one is R23, right? The distance between 2 and 3 is 1. The distance between 1 and 3 is 1 millimeter. I'll just call them R because they're equal to each other. Is that clear? So they're just sitting or standing vertically like this. No gravity. Ignore gravity. They don't just fall down. No gravity. So they just have electrical forces between them. Q1 is fixed, so maybe you pin it to the board. It doesn't move. Can't move. Q2, you pin it to the board. It can't move. Q3 could move. Q3 could move. If Q3 is exactly in the middle, what's the net force on it?
0.
0. Will it move?
No.
No, if it's exactly in the middle, it will not move. What if I disturb it slightly to the left or slightly to the right? It will move away, right? So this is called an unstable equilibrium. This equilibrium, as soon as you disturb it, it's going to go away, never come back, right? So this is going to be an unstable equilibrium. Meaning, for example, let's just, if I move my my discharge here, the force from here to here is going to be repulsive, right? They both are negative, so it's going to be pushing it this way. And from this one, it will be also repulsive, right? So it will push it this way. So the net force would be this way. So it will just move. And it will keep moving away. And it will not stop. It will just go all the way to infinity, right? Is the picture clear? So I'm going to now ask the question. The question is this. Suppose I disturb it really slightly to the right. So I don't really change the potential energy because I just disturb it slightly to the right and then you let go. What happens? It will go to infinity. Okay. It will start from 0 speed and it will go to infinity. Right? Way. The question is, by the time it gets to infinity, practically very far away, what's the speed? So find the speed of this charge when it goes to infinity. Again, 1 is pinned, can move, 2 is pinned, only 3 can move. And by the time it gets to infinity, what is its kinetic? What is its speed? What approach should we use? Conservation of energy. Don't use forces, right? Force is going to be, yeah, you will have angles, and it's not constant. So we use conservation of energy. So I think I described the problem, so I'm going to, all of them are electrons, so now it's time to solve. So conservation of energy says the potential energy at the beginning, or the kinetic energy at the beginning, plus the potential energy at the beginning should equal to the kinetic energy at the end, plus the potential energy at the end. The only the only thing that will have kinetic energy is the third electron, right? The one in the middle. The other two will not move, so they have no kinetic energy. Only the So this would be 1/2 mv squared for the third electron. Initially, what's the kinetic energy? 0. Yeah, it is 0. Nothing was moving. The kinetic energy at the beginning, potential energy at the beginning, there is potential energy between 1 and 3, 2 and 3, and 1 and 2. And at the end, there is still potential energy between 1 and 2, right? Because they don't move. So let me write it all. The potential energy at the beginning is going to be this. The potential energy between 1 and 2 at the beginning, plus the potential energy between 1 and 3 at the beginning, plus the potential energy between 2 and 3 at the beginning. The kinetic energy 1 to 1, that's 0 at the beginning. Okay. Kinetic energy at the end, that's the 1/2 mv squared. plus potential energy at the end. Potential energy between 1 and 2 at the end. Potential energy between 1 and 3 at the end. Potential energy between 2 and 3 at the end. I just wrote all of them. A lot of them are going to cancel B0. So let's look at this one. The potential energy between 1 and 2 at the beginning versus the potential energy between 1 and 2 at the end. Is it going to change? No. 1 is here, 2 is here. They're the same distance at the beginning. They're the same distance at the end. So this is going to cancel because it hasn't changed. So we could have ignored it, but I purposely wrote it. How about anything else that would be 0 maybe? The final potential energy. Yeah, the potential energy between 1 and 3 is going to be 0. Why? Infinitely far apart, and potential energy is like the product of charges over R. R is infinite, you're going to get 0. How about 2 and 3?
That's a 0.
That's another 0, right? Okay. We're ready to plug in to start substituting our variables. So for this one, I'm going to write down this. I'm going to write it this way: Q1, Q3 over R13 times K, and then plus K Q2 Q3 over R23 equals to 1/2 m v squared. By the way, when you're about to plug in numbers, it's more convenient to use K than 1 over 4 pi epsilon naught, because K is 9 times 10 to the 9. If you plug in 1 over 4 pi epsilon naught, you have to plug in the 4 and the pi and multiply by epsilon naught and do 1 over, only to get what? K, 9 times 10 to the 9. So why do all that when you can just put K? Now, what's Q1? An electron, so minus E. Q3, another minus E, so minus E squared. I'm sorry, minus E times minus E is E squared. Right? So you get K E squared over R, right? And this one you get another K E squared over the same R, right? Same R. Yeah, so K E squared over R, K E squared over R, that gives us twice K E squared over R, where R is 1 millimeter. We'll substitute in a second. So V is going to be 4K E squared over M times R. We can plug in, so 4, 9 times 10 to the 9, 1.6 times 10 to the minus 19 squared. A millimeter is 10 to the minus 3, right? If you plug in all the numbers, I think it was 1,000. It was 1,006. So I'll just write the number. So just 1,000 liters per second. Yes.
Can you repeat one more time, please? The UF, all of the UF is 0.
How far apart are they?
Infinity.
Infinity. So if two charges are infinitely far apart, this is 0. Right? You divide it by infinity. Yeah.
I would think that also kind of could be from like the potential energy is also equal to the charge times the electric potential, and the electric potential is based off of the distance. Do you know that it increases with the distance?
It does not increase with the 0. I think you're thinking parallel plates versus point charge.
You're wrong.
Yes. Okay, I think we have this. This is probably a convenient spot to pause this. And I'm going to, let me pause for a moment